You clicked for JWST's earliest supernova. Yes, that's exactly what we're unpacking. Here's the twist. If the first stars were huge, metal-free, and short-lived, why does this explosion hint at a more complex early universe? In the next minutes, we'll define the standard population 3 story, show what JWST actually picked up at extreme redshift, and reveal the clues hidden in that light. What physics lets a star die this early, yet looks so unexpected? And what does that say about how fast the cosmos built its first heavy elements? If the first stars were supposed to be rare, massive, and short-lived, why does an ultra-early supernova suggest the universe ran a more complex playbook? The standard script goes like this. After the Big Bang, the universe cooled, dark matter halos gathered gas, and the first stars, population 3, switched on roughly 100 to 300 million years in. Their fuel was simple, hydrogen and helium with trace lithium. No carbon, no oxygen, no iron. With almost no heavy elements to radiate away heat, collapsing gas had only a limited coolant, molecular hydrogen. That matters because how easily gas sheds heat sets the size of the clumps that collapse into stars. Less cooling means gas stays warm, pressure stays high, and the fragments that form are bigger. Early simulations leaned into that logic. Codes that evolved gas in tiny primordial halos found that metal-free clouds tended to split into only a few, relatively large pieces. Those clumps carried hundreds of solar masses in extreme cases, with accretion feeding them quickly. The result is a top-heavy initial mass function, skewed toward very massive stars. Not a crowded nursery, but a few giants that burned bright and fast. With that kind of mass, lifetimes shrink. A star with 30 to 300 times the sun's mass races through nuclear fuel in mere millions of years. Compare that with later generations forming in metal-enriched gas. Cooling becomes far more efficient. Clouds fragment into many smaller cores, and you get a spread of masses and lifetimes, from short-lived heavyweights to sun-like stars that survive for billions of years. This early, those first hot stars also start reionization. Their ultraviolet light strips electrons off hydrogen across growing bubbles, but the expectation has been that enrichment, the seeding of new elements, rolls out slowly and unevenly. A few explosions pollute their local pockets, while large stretches remain pristine. That baseline sets a simple expectation. The earliest environments should be clean, chemically speaking, with the telltale signs of metal-free gas in their spectra. With massive progenitors, the predicted deaths follow 2 main channels. Some end as core collapse supernovae. The truly hefty ones, in a certain mass window, die as parent stability supernovae, where intense gamma radiation creates electron-positron pairs, drops the pressure, and triggers a runaway explosion that leaves no remnant. Those parent stability events carry clear signatures. They synthesize lots of oxygen and carbon in broad amounts and can show characteristic light curves. Slow, bright rises and declines in the rest frame due to the large ejecta mass and radioactive decay of newly forged elements. In an untouched host cloud, you would not expect to see pre-existing metal absorption lines along the line of sight. Lyman alpha from surrounding hydrogen could be damped by the neutral intergalactic medium, but local metal lines should be absent if nothing enriched the gas beforehand. So the checklist seems neat. Metal-free gas limits cooling. Fragmentation favors big clumps. Those clumps make massive stars with short lives. Their first explosions appear early, with predictable timescales and spectra, and they go off in pristine neighborhoods. If you spot one at extreme look-back time, you should be looking at a clean laboratory for pure Pop-3 physics. No complicated foreground chemistry, no confusing mix of previous generations, just the raw output of the universe's first engines. That forecast gives us a clear test. Do the earliest supernovae look metal-free? Do their light curves match the slow, luminous templates for pair instability or the rapid core collapse tracks expected from massive, unenriched stars? And do their host regions lack signs of older stellar activity? Now see what JWST actually recorded at extreme redshift, because those photons carry clues that nudge this tidy model into new territory. JWST caught a supernova at extreme redshift, so early it collides with the clean Pop-3 picture. What in that light says the universe was already complicated? Here's the context. The transient popped out when astronomers compared JWST images taken weeks to months apart, a classic difference imaging approach. It brightened in near-infrared and IR cam filters, with detections spanning bands that map to the rest frame ultraviolet and optical at very high redshift. The redshift estimate comes from a sharp flux drop around the Lyman break and photometric fitting, with follow-up spectra using NIR spec for line checks when possible. In some fields, foreground clusters act as weak lenses, boosting the flux just enough to catch the rise and fade, but the light curve shape remains the key clue. Across epochs, the source appears, grows, and declines in a way that rules out a variable galaxy nucleus or a noise artifact. That's where the tension starts. At such an early time, you expect a pristine pocket of gas. Instead, the data hint at complexity. The colors evolve in a pattern more consistent with metal line blanketing than a completely metal-free atmosphere. If you compare the rise time, stretched by cosmic expansion, to theoretical templates, the match isn't neat. Parent stability models predict very slow, bright rises because so much ejecta traps light. Core collapse models run faster. The observed cadence lands in between, faster than classic parent stability curves at the inferred redshift, but with a peak luminosity that's hard to hit without some heavy element production. Look at the spectrum and photometry together. Even low signal-to-noise features can be telling when they line up across filters. A hint of ionized oxygen emission or iron group absorption would point to previous enrichment. The presence or absence of strong Lyman alpha damping helps, too. Heavy damping means a neutral environment, but if you also detect metal features, it implies a neutral intergalactic medium with a locally enriched bubble. If Lyman alpha is weak or offset while metal lines peek through, you're seeing a neighborhood that has been touched by earlier stars, not a chemically untouched cradle. The progenitor puzzle follows. Either a moderately massive star, not an ultragiant, lived fast and died young because it formed in a small, already enriched halo, or a first-generation giant exploded but mixed ejecta differently than standard models predict. A lower mass progenitor points to earlier star formation cycles and faster cooling thanks to metals, which means the initial mass function broadened sooner. A true POP3 giant should leave a slower, smoother light curve in a metal-poor spectrum, so the mismatch forces a rethink. JWST's gear makes the case possible. At redshifts beyond 10, the rest frame ultraviolet slides into NIRCam's sweet spot, so filters like F150W, F200W, F277W, and F356W trace the temperature evolution as the ejecta cool. NIR spec can chase faint emission or absorption features, even if only as tentative bumps. With repeated visits, the mission distinguishes a supernova's one-off brightening from the stochastic flicker of an active galactic nucleus, and the spatial profile stays consistent with a point-like transient superimposed on a faint host. If enrichment exists this soon, the cosmos mixed metals quickly. That could mean strong outflows from the first bursts, rapid recycling within tiny halos, or star formation that favored close multiples where feedback stirs gas efficiently. It also hints that the first stars didn't all sit at the extreme high mass end. Some may have formed at tens of solar masses and died on shorter schedules than expected for purely pristine gas. The simplest read is stark. By the time this star exploded, its neighborhood likely wasn't pristine. Rapid chemical feedback had already started, and the dawn was Messier and earlier than the neat model forecast. Which raises the next problem. What physical channels deliver that speed, and how do they reshape the timeline we use for the first star generations and their supernovae? An ultra-early supernova showing hints of prior metals tells you the universe didn't wait. It forged heavy elements and triggered normal star formation on a compressed schedule. Faster cooling, broader stellar masses, and rapid recycling moved the timeline forward. Reshaping, here's the context. The transient popped out when astronomers compared JWST images taken weeks to months apart, a classic difference imaging approach. It brightened in near-infrared and IR cam filters, with detections spanning bands that map to the rest frame ultraviolet and optical at very high redshift. The redshift estimate comes from a sharp flux drop around the Lyman break and photometric fitting, with follow-up spectra using
Thanks for watching. If you enjoyed this journey through the cosmos, hit like, subscribe, and tap the bell. And when you're ready for your next space mystery,